Okay, so time to get started. So we have one last section here to cover in Chapter 6, then we're going to go back to Chapter 4, where we skipped the 3 sections on optimization previously. Again, we talked about that before. So, what we're going to be doing in this last section is really just organizing ideas that we've already talked about. We've already shown you all of the boundary theorems, all of the lifetime theorems, I like to call them. And so mostly this is going to be a bunch of examples, and in particular how to use these diagrams. So remember, we have these diagrams. These are on page 453 of the book. So this is the R3 diagram, and then there's also the R2 diagram. So how to use these diagrams to help you in your process of, trying to decide, how am I going to solve these problems? Which of the many methods that I know from Chapter 6, hopefully, fingers crossed, will help me solve this problem? Or do I have to go back and use Chapter 5 methods? Okay. Right. So the first part is what I'm going to call diagnosis, trying to figure out, what's the right method to use. And the very first part of that is to figure out, given what you have been asked to compute, be it a line integral or a surface integral, line integral in R2, R3, whichever it might be, where are we in which diagram? And that's the very first thing to notice. So, in particular, suppose you're asked to compute a line integral in R3. Very first thing I want you guys to think is come over here and note that being that you were asked for a line integral in R3, this diagram doesn't matter. This isn't the world that the question you've been asked lives in. You've been asked a question that lives in R3, and specifically you were asked for a line integral in R3. So, looking at the diagram, the way it's put together, what are the 2 theorems that you might possibly use? And it's these 2 theorems that are contiguous with that column for line integrals. So, right off the bat, I know Gauss's divergence theorem. Not going to matter. Okay? We're not going to use Gauss's divergence theorem in this question. Right? So, I like to make this point simply because it seems like every term on the final exam, if there's a question on a line integral in R3, there's at least one student who's writing down triple integrals of divergence. So, make sure that you realize that that's a waste of time. Okay. Right, so that's, in some sense, your options. Now, next question, which of those options can I use or should I use? So, for example, can I use, let's go back to the diagram momentarily, given the line integral that I was asked to compute, can I use the fundamental theorem of line integrals? Well, in order to use the fundamental theorem of line integrals, note that given the vector field and curve that you were given for the line integral you're trying to compute, you're going to have to compute or identify corresponding things over here in column 0 in order to be able to use the fundamental theorem of line integrals. Now, can you do that? Given a curve, can you take its boundary? Sure. No problem. You're given the curve, just look at the boundary, see what it is. There might be no boundary, but nevertheless, that's something that you can determine just by looking at what you've been given. The awkward question is, given that vector field, is there an anti-gradient? And the reason this is awkward is because it doesn't always exist. Critically, this arrow points that way. So if you're here, if you have a vector field given to you and you want to know if there is a corresponding function, you're kind of trying to go the wrong way through that arrow, right? If you were given a function, you can definitely compute its gradient and find some vector field F. But that's not how it happened, and you don't even know if that's the case. You're given a random vector field. There may or may not be an anti-gradient function. Okay. All right, so this is the worry in that case. Right? And the tip-off, now we've talked through the details, but the tip-off is the arrow that you have to move backwards through. Okay. Now, same issue. Given a line integral in R3, let's ask the question, can I use Stokes' curl theorem? Well, again, there's two issues to be resolved. On the one hand, I'd need to take the vector field that I was given, and I'd need to compute the curl. Sure, go ahead. You're given the vector field. That's the direction the curl vector points, so compute the curl. Right? No problem. The awkward question is, given the curve, given that the boundary arrow points that way, can I move backwards through that arrow? Right? Is that curve the boundary of some surface? And again, sometimes there is simply no such surface. It's not just a question of whether you personally can do it. It's a question of, is there such a surface? Right? So that's the this is the concern for using Stokes' curl theorem to compute that line integral. Okay, so these are the concerns. Now, notice that this happens everywhere, no matter what you're being asked to compute. If you're being asked to compute a flux, if you want to use Stokes' curl theorem, the question is, can you find an anti-curl? If you want to use Gauss's divergence theorem, the question is there a, again, I'll call it sloppily an anti-boundary. So saying these a little bit more directly, is there a vector field whose curl is the vector field you were given? Is there a region whose boundary is the surface you were given? Right? Those are the two questions that would have to be resolved in order to use these two theorems if you want to compute a flux. Okay. Likewise, in the R2 diagram, if you're computing a line integral, you have these two theorem alternatives. In each case, you have to move backwards through one of the arrows, and moving backwards through those corresponding arrows is again the challenge. That's the question. If I wanted to use, given a line integral, if I want to use Green's theorem, I need to wonder, is that curve a boundary of some region? So one thing I want to point out to you then is that the diagrams, that again I hope you guys will all memorize and make sure that you can reproduce confidently, conveniently. Diagrams tell you what questions you need to ask, right? When you're trying to decide which of these theorems am I going to use. Diagram right here, given that you're a line integral, is telling you that curve, you're going to need to move backwards through this boundary arrow. You're going to need to answer the worrisome question of, is that curve a boundary of some region? Right? And then you look at the problem, see what you were given, and resolve it. Okay. Now, conveniently, we have a method given a vector field. If you're trying to decide if you can find an anti-gradient, we have a method for that, which is compute the curl and see if you get 0. All right, that's one of our lifetime theorems. So again, the diagram tells you what to do. If you want to decide, given, let me go back to the R3. Given a vector field, if you want to decide, is there an anti-gradient, take the curl. Because if the curl is 0, then yes, there is an anti-gradient. That's what this lifetime theorem down here tells you. Does that make sense to everybody? Okay. All right. So usually the following sort of, oh gosh, what did I just do? Usually the following method is a good general practice. And that is figure out where you are on which diagram. Right? Are you in R2 or R3? Are you computing a line integral or flux integral? What are we computing here? What are we dealing with? And thereby, knowing where you are, you know what your two theorem alternatives might be. Apply the appropriate operator to the integrand. Okay? If you have a vector field that you're computing a line integral of, if you're in R3, you're taking curl. Do what the diagram tells you to do, in other words. Right? Compute that thing. If you get 0, then you can use the boundary theorem on the left. Right? Go back to the diagram. If you're computing a line integral, if you compute curl, and if the curl is 0, then there is an anti-gradient, and you can use the fundamental theorem of line integrals. Right. If your domain is a boundary, then you can use the theorem on the right. So going back to the diagram, if the curve that you're given, the curve that you're given is a boundary of some surface. Now again, usually with boundaries, this is something that you're going to determine is kind of geometrically, given the curve. Understand what the curve looks like and then look and see, is that a boundary of something. If it is, then you can use the theorem on the right. Likewise, if you're computing a flux, if that surface you're given is a boundary of some solid, then you can use Gauss's divergence theorem. Okay. So you'll have, hopefully one of these two things will work out and you'll have an option. And then you have an appropriate boundary theorem that you can use, rewrite the problem, and hopefully turn that into an easier problem. We've seen that happen very nicely in several examples so far. Acknowledge, though, the possibility that it may be that neither of these is the case. It could be that neither of your possible boundary theorems applies. Your curve just isn't a boundary. Your function just isn't a gradient, something like that. Then you have no boundary theorem options. There are no Chapter 6 options at that point. And then you got to go back and do it the old-fashioned way. Parameterize your curve, plug and chug. Right. Maybe hope that you get lucky and there's a cool geometry fact. Maybe your vector field and your tangent vector are always perpendicular or something like that. Every so often you get lucky like that. But generally speaking, most of the time, parameterization. Okay, does everybody see the strategy here? I want everyone to see also, how it is that the diagram tells us what to do. The diagram, given what you're computing, let's suppose you're computing, I'll just stick with line integral. That tells you what your two options are, how to resolve which of those may or may not apply, yeah. All right, so I'm going to show you a few examples, and then these aren't going to take that. Oh gosh, I keep doing that. I'll show you a few examples here. Here's a question. Now, notice this question. It's not stated. Use the following boundary theorem to compute a line integral. It just says compute this line integral. We are left to decide for ourselves. Is this a Chapter 5 problem? It's parameterized. I could use Chapter 5. Is this a fundamental theorem of line integrals problem? I don't know. Is a Stokes' theorem problem? All of those are possible based on the mere fact that we're computing a line integral of a vector field in R3. So let's use our diagrams. Now we'll note quickly there are three components. So we're looking at a line integral in R3. That puts us here. That means that these are our two options. Fundamental theorem of line integrals and Stokes' curl theorem. These are the two boundary theorem options. I hope, fingers crossed, one of these will work out. So, excuse me, can I use the fundamental theorem of line integrals? Well, I need to know, can I find an anti-gradient? Diagram tells me that's what I'm looking for. How am I going to resolve that? I'm going to compute the curl of the vector field that I'm given. So, here we go. Given this vector field, I'm going to compute the curl. And it turns out that the curl is 0. Curl being 0, that means that there is an anti-gradient. That's 0. That means that there is an anti-gradient, and therefore I can use the fundamental theorem of line integrals. Is everybody on board? Okay. All right. By the way, the time will come, and hopefully pretty soon, where you don't necessarily need to have this diagram in front of you. Hopefully you'll understand that you'll have played with these ideas enough that you remember which theorem is in which sort of slot and which operators are where, and this just all happens in your head, right? So that'd be a good goal to try to reach, where you don't have to actually even look at the diagram. You just you have this organized in your mind. Before we actually do it, let's resolve the next question. Could I use Stokes' curl theorem? I mean, it's still on the table, right? Is it an option that I might consider before I make a decision on how to actually do this? Well, if that's going to be the case, I need for my curve to be a boundary of some surface. So, is it? Well, my curve is kind of ugly. Whoops, let's just do blue here. Curve is kind of ugly. But what you can do is just plug in the endpoints. Plug in t equals 0 into there. Plug in t equals 1 into there. And write down what those 2 points are. You're going to find that they are different points. So these two, the starting and ending point, are not the same. And that means that in some form or fashion, the curve looks kind of like this. It's got a starting point, and then it goes off and does I don't know what, and then it's got an ending point. And because it does not start and end in the same point, it can't be the boundary of anything. Using the sloppy language from the previous section, it has a boundary. Therefore, it can't be a boundary. Those are exclusive. Everybody on board with that argument? So, where are we? Here we go. So that means that fails because it's not a boundary of anything. So we consider our 2 options. We only have 1 option. Use that option. Right? Fundamental thermal line integrals, compute the anti-gradient, and off you go. I keep doing that. Okay. Right. Okay. How are we doing? Is everybody happy? Let me make one quick observation for you. When I computed the curl here, this is just sort of an algebraic trick that you can use for yourself. Instead of writing down the whole calculation of curl, one thing you can do is look at these 3 components, and one at a time look at the partial derivatives that you need to compute. So, for example, let's compute the first entry of curl F here. The first entry, keeping in mind that it's a little 3 by 3 determinant, etc. We're going to take the y partial of that and the z partial of that. Now let's look at those partials. What is the y partial of that? 1. What is the z partial of that? 1. I don't even need to really write anything down, right? Once you are comfortable in your mind of how to compute curl, y partial of that is 1, z partial of that is 1, 1 minus 1 is 0. Okay. And then move on to the next one. The z partial of that, 2x. The x partial of that, 2x. They're the same. The difference is 0. Fine. Move on. X partial of that is 2y. The x partial, the y partial of that is 2y. Difference is 0 again. Move on. So you can compute that without even really showing your work. Right? If at any point in that process of just kind of working this out in your head, if those 2 partials are not equal, then the difference is not 0, and then that means that the curl is not 0. And again, you're done. You can just say curl is not 0, and then move on. You know then that you can't use the fundamental thermal line integrals, and that's all you really were computing curl for in the first place. Okay. You might need to compute curl if you end up using Stokes' curl theorem, of course. All right. Okay, next one. Now this is a fun example. I like how this one works out. Again, you'll notice vector field in R3. So same deal, same options. Again, we have a parametrized curve. Gosh, it doesn't even look all that different. Curl ends up being 0. So you can use the fundamental thermal line integrals. And what happens in this case, not super interesting, happens to be if you look at where these endpoints are, you plug in 0 and 1 into this. Those 2 points are the same point. So this ends up being a really easy calculation. You turn the line integral into f of the ending point minus f of the starting point, but the ending point and the starting point are the same, so you're subtracting 2 equal things, and you get 0. So that's kind of nice. Now, that could be the end of that. I'm going to show you a different way to answer this question, and then I'm going to draw a really kind of nice conclusion at the end of all of this. Another thing you could have done, had you perchance noticed that the starting and ending point were the same point, you could have said, oh, well, then that means this is a closed curve. This curve starts here, goes off, does I don't know what, and comes right back to that same point. That means that it's the boundary of a surface. Being that it is the boundary of a surface, I could compute it. I could compute that line integral with Stokes' theorem. This line integral would be flux of the curl of the vector field. Well, conveniently, the curl of the vector field is 0. So, in fact, an alternative way to compute this line integral is to realize that it's a flux of 0, which, of course, is 0. So you get the same answer whichever way you do it, whether you use the fundamental theorem of line integrals or whether you use Stokes' curl theorem. You get 0 either way. So this is an example of a nice thing that can work out. And now I'm going to make an observation. The following observation, I'm not going to state it as a theorem, so don't cite this on an exam, right? But just for your own sort of like sanity checking purposes, if when you're looking at your options, suppose you're computing again, like in this case, a line integral. If the fundamental theorem of line integrals is an option, and if also Stokes' curl theorem is an option, if you're 2 for 2 on applicability of the potential boundary theorems that might apply, the answer to the question is 0. You just kind of think it through. I mean, we don't even need to know any more details than this. If both of these theorems apply, that means, well, then I can compute it with fundamental theorem of line integrals as the difference of 2 values. These are the starting and ending points of the curve. But if Stokes' curl theorem applies, that curve, being as it is a boundary of a surface, must be a closed curve, and therefore it starts and ends at the same point, 0. So, not a coincidence then that this turns out to be 0. Okay. So again, you can't cite that on an exam. If you determine that both theorems apply, I want to see one or the other of these. Right? You got to actually give me an argument with one of these boundary theorems showing that the integral is in fact 0. But have confidence that you did it correctly if you actually get 0. Does that make sense to everybody? Okay. All right. So there's a bunch more examples in here. I'm going to skip a few of them. They're not unlike examples we've already done. I'm going to do this one because it's a 2-dimensional example. Computing a line integral. We've got a vector field that's in R2. So, whoa, again, I do that too often. So we're up here, computing that line integral. So here's our 2 options. Right, Green's theorem, fundamental theorem of line integrals. And let's try to decide if we can use the fundamental theorem of line integrals. Well, we know from the diagram the way we're going to arbitrate this question is by computing Green's operator and see if we get 0. We can compute Green's operator at a glance. Again, looking back at the thing here, here's the 2 components. The x partial of that is 3. The y partial of that is 1. They're not the same. The difference is not 0. Green's operator is not 0, therefore this can't be a gradient of anything. So don't even think about using the fundamental theorem of line integrals. because of this lifetime theorem. Right? If it were a gradient, Green's operator would have to be 0, which it wasn't. Okay. So what is our alternative? Well, fingers crossed, hopefully we can use Green's theorem. Let's see here. We're looking at the boundary of the unit square. Is that a boundary? Well, yeah, it's given as a boundary. So I can use Green's theorem instead. Green's theorem says I can rewrite the line integral around the boundary curve as a double integral of Green's operator. Conveniently, we've already computed Green's operator. It's 2. Easy integral, done. Yes?
Do we have to cite lifetime theories when we're trying to decide whether or not we can do things?
You don't have to say, by the lifetime theorem. By the way, it's a very non-standard term, lifetime theorem. I kind of made it up, right? I think it's a fun metaphor, and I think it's the way I think about it in my head. But I do want to see, like if you say, if this is the reason you know that it's not an anti-gradient, if you say Green F equals 2, therefore not a gradient, I know where you got that from. Yeah. Is everybody good? Okay. I'm going to compute a flux. So where are we? Now we're not in R2 anymore. We're clearly in R3. Computing a flux. These are the 2 possible boundary theorems that, fingers crossed, hopefully at least one of which I might be able to use. Given where I am, I'm going to compute the divergence of this vector field and see what we get. Now you can brute force that. Here's the vector field, and you can compute the divergence. It's an easy calculation. Z minus Z plus 0. 0. Or you can observe that the vector field is given as a curl of something. And you're furthermore given the anti-curl. Now I'll do this sometimes because we don't know how to compute anti-curls. Right? So if I want you to use Stokes' curl theorem, I kind of have to, some way or another, make the anti-curl available to you. And no comment on limiting the number of different ways that I might conceivably, sneakily give you the anti-curl. But this is one possible way. I'm just explicitly telling you the vector field in question is a curl of a also given field. So that being said, I know the divergence is 0 because the divergence of a curl is always 0. Okay, so go back to the diagram. I'm given that the vector field in question is a curl of another field. So that's, again, exactly what I'm given. So that means Stokes' curl theorem is on the table. Possible that I might use. Now, what about Gauss's divergence theorem? Well, let's see here. My surface, it's part of an elliptical paraboloid, specifically part that's above the xy plane. It's this picture here, and that surface is not a boundary. Critically, the surface that I'm talking about is just the paraboloid. It's just that surface. There's this part, this sort of, that ellipse in the xy plane. That's not part of the solid ellipse there. It's not part of the surface. Right? So this is not a boundary. So seeing as it's not a boundary, Gauss's divergence theorem, not an option. Everybody good? Okay. So let's do it with Stokes' curl theorem. Again, I have the anti-curl. The flux that I'm trying to compute, I'm going to do a line integral of the anti-curl around the boundary curve the boundary curve is this. Whoops. Boundary curve is this. I got about the orientations, given the fact that this surface is oriented downward, it's sort of going the other way. Okay. Right. And so there's the line integral that I need to compute. Now, this line integral, always keep your eyes open for possible geometric good fortune. You'll notice that the vector field, that's the integrand of this line integral, points straight up. Right, or at least it points straight vertically. It's either up or down. So the vector field is vertical. The dx vector, keeping in mind that we're on the boundary curve. Which direction does dx point? Dx always points horizontally. There's lots of different horizontal directions that it might point, but it's always horizontal. So we are doing a dot product here of a vertical vector with a horizontal vector. That dot product is 0, and that makes the integral 0. Now, on the other hand, if you want to plug and chug, you can. Right? You're going to notice pretty quickly that it ends up being 0. Everybody good? Okay. Now, here's an alternative if you don't want to use Stokes' theorem. Soon as you see that the vector field is a curl of another vector field, you can also instantly conclude, oh, this vector field is surface independent. And in fact, this problem might even look sort of familiar. This looks a lot like a surface that we studied back in that previous section, and then subsequently decided that we liked this surface better and made a surface independence argument. And that works fine too. Right? So here's what that looks like. The flux over the given awkward surface is equal to the flux through this preferred flat surface. The given vector field was that. The normal vector is this. Again, geometric good fortune. Notice that the dot product here is always 0. This is always a horizontal. The vector field is horizontal. The normal vector is vertical. Again, lucky break. Dot product is 0. So either one of those methods is fine. Suit yourself. Note that using Stokes' curl theorem hinged on the fact that the anti-curl was given. If the anti-curl had not been given, this would not have been a good choice. At which point the surface independence is the only way to go. Is everybody happy? Okay. A couple more examples. These are reasonably quick. Here we're again computing a flux. We've got a vector field in R3. Go into the diagram. Computing a flux. So these are our two options: Stokes' curl theorem, Gauss's divergence theorem. And let's compute the divergence. That's an easy calculation. A couple of quick partial derivatives. The divergence is 1, which is not 0. That means that there is no anti-curl, and therefore Stokes' curl theorem off the table. Can't use it. Right? Furthermore, surface independence off the table. This vector field simply is not surface independent. You can't use that argument either. Everybody good? So fingers crossed, hopefully Gauss's divergence theorem. I need to check to see, possibly, hopefully, if the surface might be the boundary of some region, some solid region. So what was my surface? The surface is the unit sphere oriented outward. Perfect. Fantastic. Unit sphere, boundary of the unit ball. So flux, triple integral of divergence, easy integral. Everybody good? Yeah.
If they had just given us like a vector field and been like, this is a curl of something, but didn't give us the anti-curl, would that basically just be like a surface independence?
Yeah, you can still make a surface independence argument, absolutely. And in this case, this would be a weird but valid surface independence argument. So you have something, you have a surface here, right? And the boundary is nothing, right? So you can change that to any other surface as long as it has that exact same boundary of nothing. So you could say, well, I'm going to pick no surface, right? Or you could say, I'm going to take this sphere and I'm going to shrink it down to arbitrarily small and just make an argument that, well, there's no surface area. So, right. Okay, is everybody good? Okay, last example. Now this one I do just because it's kind of fun. Suppose you want to compute this triple integral. Now, a triple integral is there. There's only one possible theorem that we might be able to use, Gauss's divergence theorem. I seem to make sure that the integrand that I'm looking at, that had better be the divergence of some vector field. And, well, yeah, it's given that way. It's given as divergence of a vector field. So, fine, no problem. So I can use Gauss's divergence theorem. Specifically, I can rewrite this triple integral as a flux. Now, the question comes up, is that a win? Is this advantageous? Would I rather compute this flux? Well, I don't know. It's hard to say at a glance. But something lucky does happen. Specifically, let's look at this vector field. You see it has a common factor in here of that exponential. And factor that out. That is a simpler vector field than previously. Look at our normal vector. Do this with yellow. Our normal vector, because we're looking at a sphere, the boundary of this ball is a sphere centered at the origin, I know that the normal vector is a scalar multiple of the position vector. And what happens when you do this dot product? When you do that dot product there, you have the YZ's here, XZ's there, XY's there. That gives hope that when you do this multiplication and adding, everything will kind of match, and it does, and they all cancel, and the integral ends up being 0. So, it's not always going to work out this way, certainly, right? This was kind of a very highly manufactured example. Nevertheless, the way we resolve this question is to take advantage of the fact that Gauss's divergence theorem applies, just to give us an alternative, and then notice the alternative happens to be a good one. Any questions? Okay, so that does it for Chapter 6. Y'all have a lot to digest on Chapter 6, by the way, if you haven't already noticed. So give it plenty of time, work a lot of practice problems. Through all of those problems that you work, I hope you will take big advantage of these diagrams. I think these are very useful. Notice that they organize the boundary theorems. They show the analogies between the boundary theorems, right? They organize the operators. They show the relationships between the operators. And they show the analogies between the relationships between the operators. In other words, gradient and curl relate to each other in exactly the same way that curl and divergence relate to each other. Okay, so there's an enormous amount of information in the way that this diagram is written down and sort of put together. Okay, so take advantage of that. Yes?
Yeah, so when does this homework due?
Oh, let's see, what's today? Today's Wednesday? Yeah, we're not going to be able to collect this homework. Yeah, so now it's still assigned. Right? You still have to do it in the sense that I'm going to assume that you've done it, for the purposes of the final exam, but I won't be collecting it. Yeah, and I'll send out an email to that effect as well. Yeah. Okay. So now we're going to go back to Chapter 4. By the way, now I can. You might be able to digest the. Why did we delay that end of Chapter 4 now? Well, it's because of how much material there is in Chapter 6, and I wanted to give you as much time as possible to digest all this Chapter 6 material. Just imagine, what if the final exam were tomorrow? You know, that'd be rough. So this will give us an extra couple of days anyway for you guys to digest that material. Let me go back now to chapter 4. And here we are. Okay, so we're going to do 411. I'm hoping we'll finish 411 today. We'll see what happens. So anyway, here we go. We're going to talk about unconstrained local extrema. In general, we're going to kind of lay some groundwork for how to talk about optimization problems. By the way, those of you who are majoring in economics, optimization is extremely important in economics. Very often you want to maximize, profit. Right? Maybe you want to minimize risk, cost, stuff like that. So it's extremely important. So generally speaking, you're going to have some domain describing your parameters that you have to choose from. And it's on that domain. Each point in this domain represents a set of alternatives that you could choose from. And you want to know, of these many alternatives, which one should I do to maximize profit? So these domains might be sets. I need to develop a certain amount of terminology to talk about the various aspects of sets like this. So in particular, notice that this is a two-dimensional set that I've drawn. Analogously, there are three-dimensional subsets. There are higher dimensional such sets that you simply can't draw pictures of, but all the ideas that we're going to talk about apply equally well. So the very first thing I need to do is to distinguish points like this one, so A there, from points like this one. Well, I'll do B. So there's something qualitatively different about A and B as it pertains to this set. And both of the points are in this set. But B is kind of, on the edge or something, whereas A is, kind of in the middle-ish, right? So how do we say that precisely? I mean, I can say boundary and interior, but what does that mean, right? So we have a kind of a quick and convenient way to describe the difference. It involves using these things called balls. You guys know what a ball is. I'm going to define here an open ball of radius r centered at a point A, and it's notated like that. It's the collection of points whose distance to A is less than r. So a little small ball of some small radius r centered at that point looks kind of like that. And the way that I can distinguish the points A and B is A, and I'm just using what I have drawn in the picture here, has the feature that I can find a ball centered at A where not only is A in the set, but the entire ball also still in the set. And you can't do that with B. B, if you put some ball, no matter how small that ball is, if it's centered at B, it's going to hang over the edge a little bit. And thus the entire ball will not be in the set. So this is how we distinguish these two cases. So that's how we define interior and boundary. Now, given a side note, C is also on the boundary. It's not in the set. By the way, the little dotted line here is intended to suggest that that's where the set capital A ends, but it doesn't actually include that dotted line. So the point C is not an actual element of A, but it's on the boundary of A in the sense that no matter how small this ball is, it hangs over the edge. But it also includes always, no matter how small it is, at least one point in A. So also a boundary point. But we don't care about it because it's not in the set. Okay. So sometimes every point in the set will be an interior point. That's what we call an open set. Sometimes a set will contain its entire boundary. That's what we call a closed set. Okay. Right. This is a little bit of terminology that's going to come up here and there. Okay, a little bit more terminology. We say a set is bounded. This means exactly what you think it means. It's bounded if you can fit it inside of a ball. So, for example, this set here is bounded because it is entirely enclosed in a great big ball like that. Okay. Whereas if I were to talk about R2 itself, if I were to say, let's talk about the entire XY plane, it's not bounded. There is no ball big enough to contain the entire XY plane. Ditto the first quadrant of R2. First quadrant of the XY plane. It's just too big. You can't make a ball that contains all of it. Okay. Right, so now let's talk about what is a local maximum point. Okay, so a local maximum point of a function given a certain domain. If you can find a ball such that all of the points in that ball, which are also in the set, obviously if it includes some points not in the set, we don't care about those. But if every point in that ball, also in the set, has the property that the function is no bigger than at A. So let me show you an example. Now here I'm drawing the graph of a function, and I suggest that this point here, A, is a local maximum point because I can find a little small ball. Actually, let me do this with a better color choice. Let me use a pencil here. So A, I'm going to draw like that. Here's my small ball. There's a little small ball around A. And all of these points, all the other points in this ball, if you look at the value of the function, well, you can see on the graph here, well, they're all less than, I mean, they might be equal, but they're definitely no bigger than the value of the function at A. So the value of the function at A is the biggest value of the function anywhere nearby. You get to choose your own sense of the word nearby. Right? You can make this ball as small as you want. But there has to be some sense of nearby in which this is the largest value of the function nearby. Okay, so that's what we mean by a local maximum. So likewise, you'll notice that that point is a local maximum. A little bit different is this point. Now, that point is a local maximum, as I'm defining it here, because, I make a ball around it. Now, keep in mind we're only responsible for points that are in the ball and that are also in the set. So I'm really only responsible for these points. And of those points, is the value of the function at C at least as big as the value of the function anywhere else? Yeah, it is. It's kind of up here at the top. Right? So I'm going to call that a local maximum point as well. All right. Okay. So, nevertheless, remains that you look at these local maxima, you look at this local maximum, and there's something different between these, right? You can tell that qualitatively these are different than that one. So we are going to treat these differently. I need a way to describe exactly what the difference is in terms of the way I'm going to treat these. So the rest of this section we're going to be talking about these kinds of points like A and B, and we'll worry later in the next section about how to deal with C. All right, the algebra of how we identify and deal with points like C is very different from the algebra of how we deal with and identify points like A and B. Okay. All right, so I am going to note a definition. I need to define something called a tangent vector. So a tangent vector requires that you make a parametric curve that goes through the point A and whose velocity is v. So it's a lot easier to see from the picture. So at this point A, that is a tangent vector. The reason that's a tangent vector is because that is the velocity vector of this parametric curve that, as it meanders along, goes through A. Okay, does that make sense to everybody? So it's ends up being very useful, and we're going to see in just a couple of minutes how useful it is to have a tangent vector. Now, let's talk about at this point A what other vectors are tangent vectors. So, for example, is that vector a tangent vector? And it is. That is a tangent vector because that's the velocity vector of that curve. If I'm driving along that green curve sufficiently fast, then yeah, that is the velocity vector. The fact that it sort of sticks over the edge, that doesn't matter. We're just talking about velocity at that point. Okay? So that's a velocity vector. That's a tangent vector. In fact, given how I've drawn this point A, you might notice that at that point A, every vector is a tangent vector. Whatever direction you might need to be going, you can go in that direction at least momentarily. Okay. On the other hand, let's look at this point. At that point B, is W2, is that a tangent vector? Nope. Right? There's no way. You just can't do it. There is no way that you can stay in the set with a parametric curve that goes through the point B and furthermore has that W2 velocity. It would have to hang over the edge at least a little bit. You just can't do it. So W2 here, not a tangent vector. Now W1 is, that's fine. No problem. Right? You just have to go through that point. You kind of sideswipe that point B. You sideswipe the boundary such that at the point B you're going tangent. All right, so this is what a tangent vector is. All right, so I'm going to start now by looking at what I'm going to call unconstrained. Terminology. I skipped some terminology. Pardon me. Yeah. Where is it? Yeah. Okay, here we go. So this point A has a feature that B doesn't have. That point A, all vectors are tangent at A. Pick any vector at that point A, that vector is tangent. And so we're going to call that an unconstrained point. So it's unconstrained in the sense that when you're at the point A, you can move in whatever direction you want. At least a little bit, you can move in whatever direction you want. Okay. All right. So another way to say what we're going to be doing is we're going to start by looking at points like this. Specifically, we're going to look at unconstrained points. So when we're trying to find maxima that look like this, when we're trying to find these kinds of maxima, what we're looking for is unconstrained points that are also local maxima. So an unconstrained point, also a local maximum, unconstrained local maximum. All right, bunch of terminology. It has to get said, and now we can start talking about how we find them. The first thing I want to remind y'all is that optimization is a process of elimination. I'm not entirely sure how many of y'all are clear on this from single variable calculus, so let me take a moment to talk about how single variable optimization is a process of elimination. So here's a that's a bad picture. Let me try. Let me make a better picture here. There's a graph of some function, and between A and B, and y'all know what the method is for how to find where the maximum is. On the interior, you take the derivative, set it equal to 0, and those are your critical points, and then you check the boundary points, and whichever one is the biggest, you declare victory. So why does that work? Why is it that when you take the derivative and set it equal to 0 that something magic happens? Well, the thing is, it doesn't. When you take the derivative and set it equal to 0, if you find a point where the derivative is equal to 0, does that mean that you have found a maximum? Absolutely not. As illustrated nicely by that point. Right? So the point is the argument goes the other way. If you're at a maximum that's in the interior, then the derivative is 0. It is not true to say that if the derivative is 0, then you found a maximum. So a better way, what I prefer to say, is that when you take the derivative, what you're doing is you're trying to eliminate points like that one. You're trying to eliminate points like that one. The idea being that at a point like that, if you can identify that its derivative is non-zero, I can eliminate this point easily. There's no way that could possibly be a maximum because look, the derivative is non-zero. That means that it's going up in one direction and down in the other direction, and more to the point, it's going up in one direction. How can it be the maximum if its function's still going up? Right? So the fact that the derivative is non-zero allows me to conclude with confidence that that's not the maximum I'm looking for. So I can eliminate points by talking about their derivative. I can't really prove anything about something being a maximum by talking about its derivative. Okay. Conveniently, most points get eliminated by this method. So I can eliminate all of these points eliminate all of those points simply by observing that at those points the derivative is non-zero. So what remains are points where in reality I have no idea what's going on. I have no idea what's going on at those points. So when you take the derivative and set it equal to 0, what you are doing is finding points where you have no idea what's going on. You're not really finding maxima. You're finding failure. Right? You're finding failure to draw a conclusion. Okay. The other thing you have to worry about with this kind of thing is you have to worry about the endpoint. So in particular, the derivative being 0 argument doesn't work at the endpoints. If the derivative is, because the point is you don't know which way the function might be increasing depending if the derivative is positive or if it's negative, and is this a left endpoint or a right endpoint. So it's rather than write down criteria as to whether you do or don't have to worry about the endpoints, there's only 2 endpoints. Let's just check them. Right? So when they say that you always check the endpoints, that's why. Okay. So the big picture here, though, is that by and large what we do in single variable optimization is we eliminate possibilities and note that a simple-minded process of elimination, here in the interior the derivative is non-zero, can't be a maximum, let's eliminate it, leaves you with very few candidates that might be the maximum. So it's a great argument. It's simple-minded, but it's really effective. Okay. So when you write down a critical point, when you write down that the derivative is 0, we give them a name. We call them critical points. What you're really saying is, I can't eliminate those. Here are points that I don't understand. Okay. All right. Okay, so let's talk about multivariable optimization now. Here's how we're going to eliminate points. Some point A, We want to consider the possibility, I don't know, maybe is that a maximum? Hope that you can find a tangent vector such that the directional derivative is non-zero, and then argue just as we did in the single variable case that, well, then that can't be the maximum. If the directional derivative is non-zero, that means the function is either increasing as you move in the direction of that tangent vector, or it's increasing as you move opposite of the direction of that tangent. Either way, if the directional derivative is non-zero in the direction of a tangent vector, meaning you can move in that direction, forward or back, the function is increasing, and you couldn't possibly be at the maximum. Okay, so interestingly, now the reason I like to say optimization this way is that this creates an analogy. This is not only the way that we're going to eliminate possible maxima in the unconstrained case that we're talking about today, in the interior. This is also the same primary tool that we're going to use to eliminate possible maxima on the boundary, constrained critical points that we're going to talk about tomorrow. So I think that connection is nice, and so I like to take this point of view on it. But for the moment, we're talking about unconstrained points. Don't forget, this is how we compute directional derivatives. I need to find any vector v that makes this directional derivative non-zero. And a pretty reasonable choice to make is just choose the gradient vector, because then look what happens. If the gradient vector is the vector v, then your your directional derivative is just magnitude squared, and except in the rare instance where the gradient vector is equal to the zero vector, this is non-zero most of the time. So for most points A, with that choice of vector v, this directional derivative is non-zero, therefore A can't be a maximum, and we've now successfully eliminated the vast majority of the points in our domain. Okay, so what do we do with this? Well, we look at our failures. When does this argument fail? Here's our argument. If the function's differentiable, thus making that formula work. If the gradient is non-zero, thus making this non-zero, we eliminate the point. So when it fails, when one of those two conditions fails. This fails if the function is not differentiable. Or it fails if the gradient vector is equal to the zero vector. In either of these cases, here, our argument fails, and we can't eliminate it. So again, does that mean it's a maximum? Absolutely not. It just means that we have no idea what's going on. This is a point we can't eliminate, and so given that we can't eliminate it, we have to give it a name and deal with it later. So we call these critical points, just like in single variable calculus. Now you'll notice that I call them unconstrained critical points because by assumption we're looking at an unconstrained point, presumably in the interior of our set. Okay, so most of the time your function will be differentiable, and this won't be a problem. Like, look at this example here. That function, it's a polynomial. Polynomials are always differentiable. So condition number one, no problem. So most of the time, what you're going to be doing is taking the gradient of the function and setting it equal to zero. Find your failures. Okay, so let's walk through this example. There's the function. Want to find. Note that it's defined on all of R2. Note that every point in R2 is unconstrained. Right? R2 extends forever, so no matter where you are, every vector is a tangent vector. So take the gradient, set it equal to zero. The first component has to be zero. The second component has to be zero. And now we have a little system of equations, unfortunately a nonlinear system of equations. And we just need to find, what are the points that make both of these equations satisfied at the same time. Conveniently, this is a simple, still nonlinear, but still a simple system of equations. Y obviously has to be 0. X obviously has to be either plus or minus 1. So you get 2 critical points. That make sense? Now, let me remind you, it is not necessarily the case that these are both maxima. It is not necessarily the case that either of these is a maximum. Based on the mere fact that they're critical points. All we know is that by our little simple-minded procedure of thinking about the obvious way to eliminate a possible maximum, that simple-minded procedure has failed. So these are points simply where our simple-minded procedure doesn't give us any information. So these are points where we have no idea what's going on. All right. Another quick example. Look at this function. This function here, now in particular, I'm defining it on the closed unit ball. So when I take this function and take the gradient and set it equal to 0, I'm going to get seemingly an infinite number of critical points. But they aren't really, because think about when this is equal to 0. This is equal to 0 when x, y, and z are all integers. Right? Let's circle that better. X, y, and z have to all be integers. But this is a criterion. This is the criteria that I use to find unconstrained critical points, which means we're only interested in these solutions that are in the interior of this set. Our domain is this closed unit ball. And so there's actually only the one point that's in the interior of the set that also satisfies that gradient equation. So that's our only unconstrained critical point. Now there's a few others that are on the boundary. Those are constrained. We have a different means of dealing with the boundary. So as far as unconstrained goes, just this one. All right. Okay. So what do these various critical points look like? Here are the obvious sort of expected pictures. Critical point might be a local maximum. That's what we're kind of hoping for, right? Could be a local minimum. Well, sometimes we need to know that as well. These are not the only two options. Here are a couple more. These are just the ones that I was personally able to draw myself. And it took me a long time. They're very hard. So you could have what is classically called a saddle point. Looks kind of like a saddle. Everybody know what a saddle looks like? Right? They curve the thing so that it goes down on each side for your legs, but then kind of up in the front and up in the back so you don't fall off as easily. So that's a possibility. It's not a maximum. It's not a minimum. It's neither. But that's also not the only other possibility. This is what I like to call a shoulder point, because it kind of looks like a person's shoulder, right? So in some sense, it's, in one direction, it's kind of a maximum in that one direction, but it's kind of a inflection point perpendicularly to that. So it's not a max, it's not a min, and it's not this kind of a saddle. Right? Now, loosely speaking, just FYI, loosely speaking, all of these non-extreme, so not maximum, not minimum, critical points, loosely are all called saddle points. Because there are so many different possibilities. These are two of the possibilities. I'm going to show you a third one. I couldn't draw it myself, so I found a picture of it on a Google image search. This is called a monkey saddle. And the reason they call it a monkey saddle is because it's the way you would make a saddle for a monkey, because his tail has to hang off, right? Which is hilarious, right? It's not a max, it's not a min, it's not a, again, a classically conceived of saddle, not a shoulder. It's just this different thing, right? And then there's all sorts of different variations of weird possibilities. This one's kind of interesting. This one kind of has spots for 5. This might be a decent massage table because there's spots for your 2 legs here and your 2 arms there, and then your head can hang over the edge. But see, it's different, right? It's not there's just so many different possibilities. So you can't enumerate all of them, and so the language saddle point is just kind of an all-inclusive. We don't want to have to worry. If something like this is happening, we don't want to be responsible for classifying. The key point about these is they're not a maximum. Most of the time, that's what you're looking for, maximum. By the way, modern times as they are, very few saddles out there in most people's day-to-day life, so I like to call this a Pringle point. Right? I think that's what most people would relate to from this particular shape. So we'll see if that catches on. Okay, so how do you distinguish these from each other? Well, there's this thing called the second derivative test. You guys remember the second derivative test from way back when? Second derivative is positive. It tells you one thing. If it's negative, it tells you the other. Here's where that comes from, or here's a point of view on where that comes from. Here's the Taylor polynomial, second order Taylor polynomial. Hope you guys remember your Taylor series stuff. I know it's probably been a while, right? But you have the constant term, and then you have the linear term, and then you have the quadratic term. And the series continues, but as a quadratic polynomial, this is the second order Taylor polynomial, right? So now, if you're looking at a critical point, then the derivative is 0. The fact that the derivative is 0 at a critical point makes that term go away, right? Which makes your polynomial turn into this. And then you just argue that, well, this is a quadratic. It's either a parabola that's oriented up, or it's a parabola that's oriented down. And look at the coefficient of the x squared. The coefficient of x squared is 1/2 f double prime. So if f double prime is positive, then it's a parabola that's oriented up, which means you found a minimum. Right? If f double prime is negative, then it's a parabola oriented down, which means you found a maximum. So that's a point of view that you can take on the second derivative test. Now, there's different ways to think about it. I just like that one because it segues nicely into what I want to talk about here. We're not going to go into details on this, but this is the second order Taylor polynomial for a multivariable function. And you'll notice that it has 3 terms. It has a constant term. It has a linear term. It's linear in the sense that the power of x in here is single power of x. And it has a quadratic term. Now, this quadratic term is kind of awkward looking. Note that there's a matrix in here that's being multiplied by the x minus a vector. That product is then being dotted with the x minus a vector. So it's a weird second order term. Right? Nevertheless, it's second order because each term has there's 2 factors, each of which has a power of x. So, by the way, this matrix here, this is the matrix of all of the second partials. You guys remember partials and second partials from way back when. Now, why this is the second order Taylor polynomial, I'm actually going to leave this as an exercise for you guys to confirm, and I'm going to tell you exactly how to do it. And that is, let's start back in the single variable case. The interesting thing about the single variable second order Taylor polynomial is that this is a quadratic polynomial that agrees with f in certain key ways. This polynomial has the same value, the same derivative, and the same second derivative as the function f. And you can just write down, plug in x equals a, see what the value is, and t2 of a is f of a. Take the derivative, note t prime is f prime at a, etc. So the reason that this is the second order Taylor polynomial for a multivariable function is that this function has the same value, first partial derivatives, and second partial derivatives as the function f. So in the exact same way that this second order Taylor polynomial is defined by agreement of derivatives up to the second order, likewise this is just defined by agreement of derivatives up to the second order. And you are perfectly capable of taking the derivative, the various partial derivatives of this function, and likewise of taking the second partials of this function. And what you're going to find is that this function agrees with f in all of those derivatives. And I see that I'm out of time now, so we will pick up here next time. We're almost done with 411, not quite. We'll wrap this up very quickly on tomorrow, and then we'll do the constrained optimization. Okay, see y'all later.